All right, so today we're going to be doing chapter 32, or finishing up chapter 32 with EM waves, looking at their intensity and energy transfer. So I'm going to try to go over a lot of problems for this lecture because I know that people were a little bit shaky on intensity and power and stuff for the sound portion, chapter 16. So I want to make sure that we do plenty of examples so you can see how this stuff works. So EM waves obviously carry energy. Now here we just have the energy density for an EM wave, so it's 1/2 epsilon naught E squared plus 1 over mu naught B squared. So this is just obviously E and B are the values of the electric and magnetic field in some region because this is the energy density. Now if you remember from, I forget what chapter it was in 7D, when we did capacitors, we found that the energy density stored in a capacitor, the electric energy stored in a capacitor, was this portion right here. And now we see there's sort of an analogous portion for the magnetic field. That comes from, you can derive that from looking at inductors, and you can figure out the energy density for a magnetic field. And you add these two together, and that's the energy density for an EM wave. Now you might say, okay, when we had a transverse wave where we had an actual string or something where there was a medium, it was very obvious what was transporting the energy, right? So when we had a string that was waving, it was very obvious that the energy was traveling down the string, and that's how the energy was being transported. But what about in an EM wave when we don't have a medium? How does energy get transported? Where is the energy actually stored that's being transported? And that's a good question. And the energy is stored in the field. So that might seem kind of like a cop-out because, if we're just looking at an EM wave in a vacuum, and you say, like, well, where is the energy? And just say, well, it's just there in the wave, but you can't see it. That might seem, a little bit suspicious, and that's a fair thing to think. But so in an EM wave, the energy is actually just stored in the wave, and it doesn't even really have a definite location. So energy doesn't have a definite location in the wave. It's just stored in the wave. Now, you can get really deep into this stuff. It gets very interesting, very complicated. If you take like graduate level EM, you'll be looking at this stuff very carefully. So for now, we're just going to have to accept the fact that it's stored in the wave and leave it at that. So now let's look at this electric and magnetic field component a little bit more closely. So I'm just going to rewrite our energy density formula. Now we know that we can we know that the electric and magnetic field are related by the speed of light. So I'm going to replace the magnetic field here with E over C. So let's replace this with E squared over C squared. And then we know that since C is equal to 1 over mu naught epsilon naught square root, let's replace also this 1 over C squared. That means 1 over C squared is mu naught epsilon naught. So now I'm going to replace this C squared with mu naught epsilon naught. So this I'm going to replace with, I'm going to have mu naught epsilon naught and then times the E squared. And now we can see that something interesting happens. Our terms are exactly the same. Right? The mu naught cancels, and we get epsilon naught E squared. So epsilon naught E squared for our energy. So now we actually see that the energy stored in the electric field component is exactly the same as the energy stored in the magnetic field component, even though the magnetic field magnitude is so much smaller than the electric field. You might think that the energy stored in the magnetic part is going to be way less, or a factor of C less, but it's actually not. They store equal amounts of energy. So half of the energy when we have an electromagnetic wave, half of it is stored in the electric field, and half of it is stored in the magnetic field, no matter what their magnitudes are. So now let's get into the energy, how it's transported. So we know that electromagnetic waves are obviously traveling waves. That means that we can talk about the energy transferred per unit time, per unit area. This is just another way of saying the power per unit area. So let's say we have some surface. So just like we did with when we did like sound intensity and the power of sound. So let's just say I have some arbitrary surface here, which is my blue circle. So I have some arbitrary surface here, and I have electromagnetic energy. There's some source inside of it, let's say, and I have electromagnetic energy coming directly out of this circle, directly out of this sphere, so that the direction of the energy being transported out, right, the energy is flowing out away, is perpendicular to the surface, right? The surface is here, and at every point, the energy is perpendicular to this surface. And then since the electric and magnetic fields are obviously a wave, they're changing their magnitude at each point in time. So what we want to do is we want to talk about for a unit area, so like some unit area here for this whole surface, per unit area, per unit time. So we're looking at the instantaneous rate of power leaving a unit area. And so we want to develop a quantitative way to talk about this. Okay, so let's look at an electromagnetic plane wave. So here we have just an electromagnetic, there's a wave coming this way. You have your electric field oriented in the y direction, the B field oriented in the z direction, and it just looks like a plane wave like we did in the last lecture. So we want to know, let's look at, let's just take some random plane here. So we just have some plane in the YZ axis, and this is like our unit area. And we want to figure out how much energy basically moved through this unit area in a unit time dt. Okay, so we want to know how much energy came from over here, passed through this area A, and is now on the right side of the plane in a time slot dt. So, and in time dt, the wave, let's look at a specific point on the wave. Let's say it was right on this plane here, and then it moved to this location right here, and we have a new plane that we're looking at as well. So we're looking at just this little region here, and I want to know how much energy is stored in this little rectangle here. So I can write that as du. So that's my total energy stored, is the energy density times the volume. And since we're just looking at a very small moment of time, like an infinitesimal moment of time, we're just looking at the differentials, right, du and dv. So what is dv first of all? So dv is going to be this little distance here, right? How far it traveled down the x-axis, and then this area here, right? So this wave moved from this location to this location, and we know that velocity is equal to distance over time, and we're looking for the length x here. So distance is equal to velocity times time. And we know, let's call this dx since it's a very small unit. So we know that the velocity is obviously c since it's an electromagnetic wave, and we're going to have some little time interval dt. So in time interval dt, this wave has moved from this location here, whatever, was here at time 0, and then a time dt later, it was right here. So it has traveled c times dt distance down the x-axis. So dv we can write as the x direction, so this. So we've got c dt times the area of that plane, and that will give us the volume within here. And then we know that the energy density, we just did that in the previous slide, we know that the energy density we can write as epsilon naught e squared. We want to just write it only in terms of the electric field for now. And then we'll replace dt with c dt times a. So we'll write it like that. And now remember we said here that we want the energy per unit time per unit area. So the energy per unit time would be du dt, right? And then per unit area would just be another 1 over the area. So this will give us the energy per unit time per unit area. And luckily, it looks like we can end up with that. right? So if I just move my dt over to this side, and then I just divide by a, I can move those two to that side, and I'm left with c times epsilon naught e squared, right? And so now this is my energy per unit time per unit area. So it's how much energy is moving through a unit area per a unit time. Okay, so now I'm going to take this equation here, and we're going to rewrite it a little bit. So we have the 1 over a du dt is equal to, we said c times epsilon naught e squared. So first I'm going to rewrite my c as the square root of epsilon naught times mu naught, and then I'm going to replace one of the e's with c times b. So not both of them, just one of them. So I'm going to have c times b times e still. And now this c here, let's also replace with 1 over mu naught epsilon naught. So this will give us, we're at epsilon naught from up here. And then we have now square root mu naught epsilon naught, so that gives us, that's squared. And then we have b times e. And we can see that obviously our epsilon naughts cancel. So we're left with, I'll write it as e times b over mu naught as our energy per unit time per unit area. Now this actually corresponds to a vector. Here they look, since we didn't derive it using vectors, it's not obvious that this quantity actually does correspond to a vector. But you can derive it, like I said, if you use the differential form of Maxwell's equations and you do it with vector calculus, you can derive it as a vector. But obviously we didn't do it that way, so it's not clear to us that this is a vector. But remember, if you have, we know that the electric and magnetic field are perpendicular, right? So if you have two vectors, A and B, that are perpendicular, their cross product will just look like the magnitude of A times the magnitude of B. So that's actually what is going on here. This corresponds, this is the magnitude of a vector. And that vector is called the Poynting vector. So the Poynting vector tells us the direction of energy flow for an electromagnetic wave with an electric field component E and a magnetic field component B. And now the important thing here is to realize that this is, all of these vectors depend on space and time. So this is like an instantaneous snapshot of the energy being transported. So really all of these, all three of these vectors, right, we know the electric and magnetic vector wave functions depend on both the location and the time, so the Poynting vector does as well. Now remember, our power is the total energy flow over some surface. So if we take the integral, a surface integral, a closed surface integral, so we're doing the integral of the Poynting vector over some closed surface, just like we did with Gauss's law where we always needed a closed surface. If we take the integral of the Poynting vector over some closed surface, that will give us the power that's being, the total power that's being transmitted by the electromagnetic wave. And again, this is the instantaneous power because we're just looking at a specific moment in time. So we said that the Poynting vector is a function of space and time, so it's going to have like an x and a t. So just integrate that over your surface at that moment in time, and that will give you your total power moving through that surface. So now think back again to 7D, and this integral here looks a lot like flux, right? When we had electric flux with Gauss's law, and when we had, remember we had E dot dA was the, was the electric flux, and then we had B dot dA was the magnetic flux. So whenever you take a vector field, integrate it over a closed area, a closed surface, that's a flux. So this is actually our energy flux. So we can actually think of this integral, or we can think of the power here, as the energy flux. And that would mean that our Poynting vector is like the energy flux density. Okay, so that's the total energy, the total instantaneous energy flowing out of some area at a specific moment in time. So now if we take actually the average value, so instead of looking at a specific moment in time, we take the average of this vector over a complete cycle, that will give us the intensity. So let's rewrite, we have our pointing vector here. And also, just keep in mind that we know that the electric and magnetic field are always going to be perpendicular. So the only point of writing it as a vector is just to tell you what direction it's in, because the pointing vector, since it's a vector, obviously, it has a direction. It tells you what direction the energy is flowing in. So that's really the only purpose of like the vector part here, because these are always going to be perpendicular. So you never have to worry about like a sine theta in here, since our electric magnetic fields will always be at that 90 degrees. So anyway, so we've got this. So let's take the average value. So let's write just some random electric field here. And we'll have also just some, some arbitrary magnetic field. Okay, so since both of these, since this wave is obviously moving in the x direction, we know that our pointing vector is going to be in the x direction because the pointing vector transports energy. It obviously has to transport energy in the same direction that the wave is moving. So let's just make our electric field in the j direction and our B field in the k direction. That way we have j cross k is I. So everything makes sense there. Okay, so now let's write this out. So we have 1 over mu, we've got E max times cosine kx minus omega t. Move this down here. And then we have B max times cosine kx minus omega t. And like we said, we have j hat cross k hat gives us I hat. So we know that the pointing vector is in the I hat direction, which is in the same direction of travel for the wave. And then let's just multiply these out. So we have 1 over mu naught, we've got an E max, a B max, that's just the amplitude, and then we have a cosine squared. So we've got cosine squared kx minus omega t. And now remember from a couple of chapters ago, we want to take the time average of this. So we want to figure out what is the average value of cosine squared over one entire cycle. And we know that the average value of cosine squared over an entire cycle is 1/2. So we're going to replace this cosine squared with 1/2. So we've got this now. We have E max, B max over 2 mu naught. So this is the intensity, which is the average value of our pointing vector. So this is important, that's for a sinusoidal electromagnetic wave, because I obviously use the time average value of cosine squared here, so I assume that these were sinusoidal. So for a sinusoidal electromagnetic wave, the average value of the pointing vector is the intensity of that wave, and it's given by the maximum, the amplitude of E, and the maximum amplitude of B, divided by 2 mu naught. And now obviously you can rewrite this in a bunch of different ways, since we know mu naught is related to C and epsilon naught, B is related to E and C, so these are just some other ways of writing it. So whichever way is most appropriate for your problem, depending on the numbers and variables that you have, use whatever. So here I just did, this is just a little recap. So you have the instantaneous value of the pointing vector, which is the energy per unit time per unit area, or the power per unit area, and that's an instantaneous value at a specific time t. Or when we take the average value of the pointing vector, that's the intensity. So it's basically the exact same things here, except one is the instantaneous value and one is the average value over a whole cycle. All right, so now let's do an example. So here we have for the non-sinusoidal wave described in section 32.2, so that was just some random wave, I don't think we need it. Suppose that E is 100 volts per meter, find the value of B, the energy density U, and the rate of energy flow per unit area S. Okay, so the first thing we want to do is find the value of B. Well, for B, we can just do E divided by C. So we get 100 volts per meter divided by 3 times 10 to the 8. So that comes out to 3.33 times 10 to the negative 7 Tesla. And then we want to find the energy density U. So the energy density, we can just use this formula since we know E. So that will just be 8.85 times 10 to the negative 12. And then we have 10 squared for 100, right? I'm just rewriting 100 is 10 squared, and then square that. So that will give us, we'll have 10 to the 4 here, 10 to the negative 12, so we'll get 8.85 times 10 to the negative 8. And this is in joules per meter cubed since it's an energy density. And so now for the last part, they just want us to basically find the magnitude of the Poynting vector. So the Poynting vector we know has magnitude EB over mu naught. So this will just be 10 squared. And then B we said was 3.33 times 10 to the negative 7. And then mu naught is 1.25 times 10 to the negative 6. So this comes out to 2.65 watts per meter squared. Okay, so we've got this, and this. Sorry, this is 26.5, not 2.65. So that is 26.5. Okay, now let's do one more example with this. So here we have a radio station on Earth's surface emits a sinusoidal wave with average total power of 50 kilowatts. Assuming that the transmitter radiates equally in all directions above the ground, find the electric field and magnetic field amplitudes Emax and Bmax detected by the satellite 100 kilometers from the antenna. So here they're telling us, first of all, that the power is 50 kilowatts. And they're telling us also that the area we're going to look at, so since we want to find, we're going to have to find the intensity. Remember, intensity is power over area. The area we're looking at is only going to be a half circle because they're saying basically pretend that no energy is lost into the ground. It just takes up kind of like a half sphere above the ground. Even though it's not realistic, for this problem, we'll use that. And then, so the distance we're looking at also is 100 kilometers. So that's 100 times 10 to the 3. So that's going to be 10 to the 5th meters. So if we want to find Emax and Bmax, we can look back at this equation, and they give us the power, right? They give us the total average power, and we know that intensity is also power divided by area. So if we have the power and we know the area, we can find S average, and if we have S average, we can find Emax and Bmax. So that's what our plan of attack is going to be here. So first, let's find the intensity. So the intensity is going to be, the intensity is power over area. So the power is 50 times 10 to the 3. The area is half a sphere. So a full sphere is 4 pi r squared. So we're only looking at 2 pi r squared. So we've got 2 pi r squared. And then let's just plug this in. The r squared is 10 to the 5th squared. So this comes out to 7.96 times 10 to the negative 7. And this is in watts per meter squared. Okay, so now we want to find the Emax and Bmax. So we know that this is also equal to S average now, which is equal to Emax Bmax over 2 mu naught. So since we obviously can't solve for both of these, if we only know S average, we obviously can't solve for two unknowns with only one equation. So let's just go back here and see, we have a bunch of equations that only involve E, and then once we get E, then we can translate that to B. So So let's use this one here since that's the first one, so why not? So we have the intensity is equal to E max squared over 2 mu naught C naught. So we're going to find E max is going to be I times 2 times mu naught times C. Okay, so for E max, we'll have 7.96 times 10 to the negative 7 times 2 times mu naught is 1.25 times 10 to the negative 6, and then 3 times 10 to the 8 square root, and that comes out to, okay, so this comes out to 2.45 times 10 times 10 to the negative 2 volts per meter. And now let's do the magnetic field. So B we know is going to be E over C, so we can just take our previous number, 2.45 times 10 to the negative 2 we said, yeah, and then divide it by the speed of light. So this will give us 8.17 times 10 to the 11 Tesla. So this is our B max, and then we had our E max right here. Okay? So it's important here to note that they gave us the average power, right? So they told us that this 50 kilowatts was the average power. If we had the instantaneous power, we wouldn't have been able to use S average because you can't mix if you have an instantaneous power and an average intensity. That doesn't really make sense to mix those two. So we needed the average power in order to make that I equals P over A substitution in this first step right here. Okay, so now let's move on to something that seemingly breaks Newton's laws. So let's say so we're going to use a little bit from 7D here again, so I'm sorry if you guys thought you were done with the Biot-Savart law. So let's say that we have a charge here, so we'll call this Q1, and it's moving in this direction with some speed v. And we have a charge here, Q2, and it's moving in this direction also with the same speed. So they have the same, let's say the same charge, same magnitude, same velocity, or same magnitude of velocity. So let's find the force on Q2 from Q1. Now it's going to have both an electric and a magnetic component, since they both have an electric and magnetic field, since they're charged and moving. So the electric force for both will just be in opposite directions, right? So that seems fine so far, right? Because they're they're the same charge, so they want to just repel each other and go in different directions. So the force is going to kind of be just pushing them away from each other, the electric force. So now, let's look at the magnetic force. So remember, Lorenz's law is QV cross B. So for this particle, so let's find the magnetic force on this particle from Q1. So you can do your right-hand rule a bunch, and you'll see that the magnetic force on Q2 due to Q1 is in this direction. So I won't bore you with the right-hand rule. You can do it yourself and verify. And then we have the magnetic force for from charge 2 on charge 1 using the right-hand rule is in this direction. So what ends up happening, so now you can see, since these particles had the same velocity and same charge, the forces are going to have equal magnitudes, but they're obviously not going to be in the same direction, right? So if we add up, if you add up the resultant from these two and then the resultant from these two, they're clearly not going to be in the same direction. So now why is that? Because it seems like, from Newton's laws, we should have that, we have equal and opposite forces, which is very closely tied to momentum conservation. So it doesn't seem like here momentum is conserved because we don't have equal and opposite forces acting. And the reason that is because the electromagnetic field itself actually carries momentum. So the EM field carries momentum. or the field itself has a momentum. So anytime you have a particle that has an electromagnetic field associated with it, so in this case, they both have an electric and magnetic field component, um, those fields themselves have momentum in addition to the particles themselves having momentum. So now this might seem very odd because we're used to writing momentum as P equals mv. And how does just a wave that has no mass, right? Light, you know, light doesn't have a mass. So how can a wave that doesn't travel through any medium, is massless, how can it possibly carry momentum? And this is very closely tied to relativity. When you take, I'm not sure if there's a specific relativity course, but when you start doing relativity, you see that there's momentum in these fields and that you don't actually need to have mass to have momentum. So this is like the Newtonian version of momentum. When you get into relativistic physics, momentum actually takes a different form, and you can have particles with no mass that still have momentum, which is what an EM wave has. So the EM wave carries momentum even though it has no mass. So now let's figure out what's the momentum density of this, because obviously we're going to want to talk about this quantitatively. So we want to find a formula to talk about how much momentum an EM wave carries. So your book gives you the momentum density for an electromagnetic field. So they just give this to you. They don't derive it or anything, so you can just take it as a given. So the momentum density dp dv is given by the Poynting vector over c squared. And now let's look at our the same diagram that we had before, and let's do the same thing where we switch dv, because we know how this length here, we know the side x, and we also know the area. So let's switch dv. We're going to replace dv by c dt times the area again. So that's going to give us dp over c times a dt. So let me rewrite that actually. So I'm just replacing dv with c dt times a. So that will give me 1 over c times a. dp dt is equal to s over c squared. So now we have the rate momentum's changing with respect to time. So let's cancel out c. So we have a c on each side. So we have 1 over a now. dp dt is equal to s over 1c, right? So just a single c now. And so now this is our momentum per unit time per unit area again, right? Because we have the momentum change per unit time and then per unit area. So this gives us the momentum flow per unit time per unit area in an EM wave. So that's just right here. And again, this is the instantaneous value of the Poynting vector. And now if we want to find the average momentum flow rate by changing this to the average value of the Poynting vector, we can do that too. So let's replace, so we have 1 over a dp dt is equal to s instantaneous over c. And now we want to replace that with the average value. And now this on the left here, this dp dt, think back to like 7c or something, where the force, remember force is also the change in momentum. So force is dp dt as well. So we can replace this with the force, and then we can see that we have a force over area, or a force per area. And in our like mini lecture on chapter 12, we said that a force per area is a pressure. So this left-hand side of our equation actually corresponds to a pressure. So I'll call that P rad. So we have a lot of P's now. So this is the P for pressure, not momentum. So this is a pressure, and it's a radiation pressure. So this equation, so S average over C, remember S average is also equal to the intensity. So the intensity, the average intensity divided by the speed of light gives us a pressure. And that's because if the fields have momentum, when they hit something, they're going to have a pressure too. So this is the pressure associated with that momentum in the fields. So the pressure is equal to the intensity over the speed of light if the wave is fully absorbed. So if whatever surface the electromagnetic wave is hitting, if it's completely absorbed by that surface, this is the radiation pressure. So it's absorbing that momentum essentially. Now, if it's reflected, so if you have some kind of surface that's highly reflective and it actually reflects the EM wave, the pressure will just be twice that. You can kind of think of it as if it's just absorbing, just kind of get hit once and that's it. But if it's reflecting, the change in momentum is basically twice as big. So P rad is equal to 2 times the intensity over the speed of light. So this is if the wave is reflected. And so I forgot to type up these 2 equations, but you should definitely, they'll be on your formula sheet for an exam anyway. But, just keep these in mind. But anyway, so you can kind of, like I said, sort of just take some of these as a given. So the radiation pressure when the wave is absorbed by your surface is given by this, and the radiation pressure when it's reflected is just given by this. Okay, so let's do an example with this. So here we have an Earth orbiting satellite has solar energy collecting panels with a total area of 4 meters squared. If the sun's radiation is perpendicular to the panel, so that just means it's hitting it. Remember, our pressure is the perpendicular component of the force. So they're just telling us we don't have to worry about components really. But anyway, so find the average solar power absorbed and the average radiation pressure force. So the force of the radiation associated with the radiation pressure. So first things first, let's just write down what we have. So the area is 4 meters squared. We want to find the average solar power absorbed. So here we just need a little bit more information. So this information is listed in your book. The intensity of the sun's light at the basically the edge of the atmosphere. So that's just given to you in the book. So that intensity is 1.4 times 10 to the 3 watts per meter squared. So we're going to need that for this problem. Because obviously if all we had was the area of this, the solar panels, we wouldn't really be able to do much. So in your book it has this. So this is the intensity from the sun's rays at the surface, or like the outer edge of the atmosphere. And now we're looking for the power. So now we have the area and we have the intensity. So we know that, remember, intensity is power over area. So we know that the power is just the intensity times the area. So now we can just multiply, since we have the intensity, since the satellite is essentially just orbiting right outside our atmosphere, we can use this and then multiply it by the area of the solar panels, which was 4 meters squared. We can find the total power absorbed. So that's going to come out to 5.6 times 10 to the 3 watts. Okay, so now we found the average solar power, and the reason it says average solar power, again, is because we're using intensity, and intensity is associated with the average energy. So now they want us to find the average radiation pressure force. So I know that that wording might be a little bit confusing, but basically all they're saying is what is the force. So when we said that, so now I have a lot of P's, so I'll write P rad again. So we have this P is for power, and this P is for pressure, so we have to be a little bit careful with our letters here. So remember that the pressure is force over area. So they're just asking what is this force here. So find the radiation pressure on this satellite panel, you know the area, and then just calculate the force. So we want the force is equal to P rad times the area. And P rad, so the pressure, is just going to be right here. Oops. I over C, the intensity over C, because on a solar panel, obviously it's going to be absorbed. So this P rad, let me do that here, is I over C. So that's going to be the intensity, which we had in the book was 1.4 times 10 to the 3. C is 3 times 10 to the 8. And this comes out to 4.7 times 10 to the negative 6 pascals. So now we can just plug this pressure into our formula right here for the force, since we have the area as well. So the force is just the 4.7 times 10 to the negative 6 times the area we said was 4. So this comes out to 1.9 times 10 to the negative 5 newtons. So that's obviously not very big, but when you're talking about satellites that could be in orbit for like years, this can actually have an effect. So anyways, I know this question, the wording was a little bit weird at the end, and you just have to be very careful of like all the averages versus instantaneous. But okay, so now what we're actually going to do is we're going to go on to EM standing waves. So that's it for the pressure and intensity for now. Well, we're going to do it for standing waves also, but that's the end of the new information about pressure and intensity. So now let's look at EM standing waves. Okay, so now for an EM standing wave, things are a little bit different than in the case of like the plane wave that we looked at last time. So you can see here we have a EM wave traveling, and then we have a perfect conductor in the YZ plane. So whenever we talk about standing waves, we're going to have perfect conductors because they completely reflect an EM wave. So those are going to be like our endpoints, are a conductor. And you can see that the magnetic field here, so these waves are no longer in phase, right? When we had a plane wave, they were perfectly in phase, but now they're not. And you can see that here, the magnetic component is non-zero on the conductor, but the electric component is 0 at the conductor, right? So this one goes to 0, the magnetic field is non-zero. And now this is because, so this wave here, so our electric field we can see is in the y hat direction, right? This wave is obviously pointing in the y hat direction or the negative y hat direction, doesn't matter for now. So this is obviously in the y hat direction, and then our magnetic field is obviously in the z hat direction. And now the reason that the magnetic field is non-zero at the conductor and the electric field is because the electric and magnetic field interact differently with the conductor. So they basically, they're called boundary conditions. So they have different boundary conditions when they meet a conductor. So an electric field, the perpendicular component of an electric field at a conductor is going to be non-zero, but the parallel components will be 0. And we can see here that our electric field is in the y direction, and our conductor, that's certainly parallel to the surface of the conductor in the y direction. So our electric field has no component in the y direction because of the way that electric fields interact with conductors. Now the magnetic field is exactly the opposite. So magnetic fields, their perpendicular component is 0 at the surface of a conductor, but the parallel component is non-zero. So that's why here our magnetic field, which is oriented in the z direction, can have a non-zero value at the surface of the conductor, is basically because of these boundary conditions, which just say that the different components of the electric and magnetic field interact differently with a conductor. So understanding where these boundary conditions at the surface of a conductor come from are like way beyond the scope of our course. I'm just telling you these are the boundary conditions, and that's why the electric and magnetic field basically are out of phase now when they hit a conductor, is because they interact differently with that conductor. So now let's write a wave function for our standing wave. So we're going to have for the electric field will be E max times cosine kx plus omega t, and this is because we know for a standing wave we have one wave traveling in the negative x direction and then another wave traveling back out in the positive x direction. So we're going to have plus omega t here, and then we have that inverted wave going in the positive x direction. So then we're going to have minus, for the inverted wave, cosine kx minus omega t. And let's say that this is oriented in the j hat direction, like we said before. So we have, okay, now let's do the b. So b, we're going to have b max, and then we're going to have cosine kx plus omega t. And we know that this wave here, when it's kx plus omega t, is traveling in the negative x direction, right? So this is traveling, we're going to have E cross B is in the negative I hat direction, and we said that E was in the j hat direction. So if we have j hat cross something is negative I hat, that means that our magnetic field has to be in the negative k hat. So j hat cross negative k hat is equal to negative I hat. So that means that this cosine actually gets a negative, because if it's if this portion of the wave, this wave traveling in the negative x direction, has an electric field that's oriented in the j hat direction, that means that the magnetic field has to be oriented in the negative k hat direction so that you get the proper direction of travel when you do E cross B. And now here we are going to do the same thing. So for this portion of the wave, we have it's in the negative j, since this was negative j. So negative j cross something is the positive I hat direction, right? Because now we're looking at the wave that's traveling in the positive x direction. So the E component is oriented in the negative j hat. So negative j cross what will give us a positive direction, positive x hat direction of travel. So negative j hat cross negative k hat will give us positive I hat. So this is negative k hat. So we're going to have another negative here, cosine kx minus omega t, and this is all k hat. Okay, so now let's simplify this a little bit. So let's just take this and move it over here. So let's find the standing wave equation here. So we're going to use a trig identity, and it's that cosine of A plus minus B is equal to cosine A cosine B minus plus sine A sine B. And so for our A and B, we'll have kx omega t. And so then for each, so now for each cosine in here, we're going to break it up into cosine AB and sine AB. So let's just do that. So let's be careful with all our negative signs. So I'm going to ignore Emax for now, just so that we don't get confused and just look at the cosines. So for this first term here, we're going to have cosine A is kx, cosine B is omega t. We're going to have minus sine kx, sine omega t. So then for the second cosine term, we have, let's see, minus, put it all in parentheses, we have cosine kx, cosine omega t, and then it's minus omega t, so the minus here corresponds to a plus here, so we do plus sine kx, sine omega t. Okay, so now let's simplify this so we can see that our cosines will cancel, right? Because we have cosine minus cosine. And then this negative sign will change a negative sign here. So we're going to end up with negative 2 Emax from before, because I left that Emax out, sine kx sine omega t. So this is the equation for our electric field standing wave. Now if you want, you can do it, I'm not going to do it for the B field because it's essentially the same, so it'd be a good idea to try it out. Work with the trig identities a bit. So now that we have this, let's look at where our nodes and antinodes are. So I'll just write it down again. So we have negative 2e max sine kx sine omega t. So we want to find where the nodes are first. So let's look at the nodes first. And now let's just draw, let's say this is our conductor here. So this is our conductor. We know that the electric field, because we said with our boundary conditions, the electric field is always going to be 0 at our conductor, right? Because its parallel component has to be 0. So our node will always at least be at x equals 0. So it's essentially similar to that string that's tied down at one end. So we're going to have the same thing that we had with our transverse strings, where sine kx is equal to 0 for a node. And we can see that that's going to happen at 0, pi, 2 pi, 3 pi, 4 pi. So it's going to happen at integer values of pi again. Right? So we can say, okay, kx is equal to n pi, and x is n pi over k. And we know that k is 2 pi over lambda, so those cancel, and we end up with n lambda over 2. So we have nodes at every integer of half wavelength. So we're going to have a node at 0, lambda over 2, lambda, 3 lambda over 2. So every half wavelength, we're going to have a node. And now what about the antinodes? Well, the antinodes, so antinodes will be when sine kx is equal to plus or minus 1, right? So we'll have sine kx is equal to plus or minus 1. And now that happens at n plus 1/2 values of pi. So we have kx is equal to n plus 1/2 times pi, which gives us x is equal to n plus 1/2 pi over 2 pi lambda. And this cancels to give us values of x at n plus 1/2 lambda over 2. So that means we're going to have an antinode at lambda over 4, 3 lambda over 4, 5 lambda over 4, and all the odd integers then. So here are our antinodes, and here are our nodes for the electric component of the standing wave. And now let's look at the magnetic part. So if you go through all the trig identities, so take if you take this, now this is different because it has an extra negative sign here. Use the same trig identity, you're going to find that the magnetic component actually looks like this. It's actually going to end up being cosine kx and cosine omega t, as opposed to the electric, which was sine kx and sine omega t. And that's because we said here at our boundary, we can see that the electric field was at 0 at the boundary, so it has to be a sine function in that case. And our magnetic field was not 0. You can see clearly here it's at an antinode, so that means it's going to be a cosine function. So if we want to find the nodes and the antinodes of cosine now, so if our conductor is here, our magnetic field is going to look like that, right? It's going to be a cosine function. And you can also kind of just look at our diagram here, and you can see that wherever there's a node for the electric field, it corresponds to an antinode for the magnetic field, and vice versa. When you have a node for the magnetic field, it's an antinode for the electric field. So now you can do the same thing that we did for the electric field, where we actually used, we actually calculated what the values were here, or you can just say, well, I know that the nodes and antinodes are going to be swapped, so the nodes for B are going to be at n plus 1/2 lambda over 2, and the antinodes are going to be at n lambda over 2, just opposite the electric field. Okay, so here's just a recap of our standing EM waves. So here is the equation for our electric component and our magnetic component. And it's important to remember that your electric field at a conductor will always be 0 for our standing waves, and the magnetic field will always have an antinode, so it will always be at its maximum amplitude at the conductor. And this we solved assuming that there was a conductor at one end. So now what happens if we put a conductor at both ends? So that's called a cavity. So let's say we have now a conductor at two ends here. What kind of wavelengths will be allowed? Well, we know for the electric part, right, it can definitely fit like half a wavelength, right? We can fit half a wavelength like that. You could also fit a full wavelength. We could also fit like 1.5 wavelengths. So you can see that we're fitting half wavelengths just like we did with those pipes. So the minimum value we can fit is 1/2 wavelength, and then all the other values we can fit are just multiples of that half wavelength. So that means that the length of our cavity has to be an integer multiple of a half wavelength. So n lambda over 2 has to be the length of our cavity. And that means that we can have possible wavelengths. So if we just solve this for lambda instead, that means that we can have possible wavelengths of this value, 2L over n, where n is just an integer. And this is, again, just like what we did with the harmonics and the pipes. It's the exact same idea. So these are the allowable wavelengths in a cavity of length L. And then there will also be corresponding frequencies to that. So we know that the frequency is given by the velocity over the wavelength. And the wavelength we can just replace with 2L over n. So that will be C 2L over n. And so these are our allowable frequencies now, where again n is equal to a integer. So these are our normal modes of a standing EM wave in a cavity. So I just rewrote that here for you. So here we have a cavity of length L. These are our allowable wavelengths. And then the frequencies associated with those wavelengths are just given by this here. So now let's do an example. So for this example, let's find the intensity of a standing wave. So we have the intensity we know is S average, the average of the pointing vector. And we know that the instantaneous pointing vector, so the pointing vector at a specific moment in time, is 1 over mu E cross B. So let's write down our standing wave equations. So we have sine kx sine omega t, and for B we have cosine kx cosine omega t. They might be able to guess already what the answer is going to be, but let's go through it and make sure that our hunch is right. So let's take the pointing vector at a moment in time. So all we have to do is just multiply our electric and magnetic field wave functions together, since we know that they're going to be perpendicular. We don't have to worry about this cross product here. So we're going to have 1 over mu naught. Then we're going to have, let's see, 2, I'll just call this E for Emax right now, times sine kx sine omega t. And then we have 2b cosine kx, and then cosine omega t. So now we want to find the average value of the pointing vector. So this is our pointing vector at a specific moment in time. So the average value, we're going to take the time average, which means what's the average value of these trig functions over a whole cycle? Well, if you draw one out, so let's look at sine. If you average this out over a whole cycle, the average is just going to be 0, right? Because it goes up to +1 and then it goes down to -1. So the average is just 0, whereas before when we had that sine squared, it never went to the negative side, right, because we were squaring it. So the average value was 1/2, not 0 down here. So the time average is actually all 0 for each one. So our average intensity of a standing EM wave is 0. And now this makes sense because we said when we did transverse standing waves, we said that a standing wave doesn't transport any power, right? Because it's not going anywhere. The wave's not traveling, so it can't transport any power. So it makes sense that the average intensity of a standing EM wave would also be 0. Okay, so now let's do an example with this. So we have an electromagnetic standing waves are set up in a cavity with two parallel highly conducting walls 1.5 centimeters apart. We want to calculate the longest wavelength and the lowest frequency of these standing waves. Okay, so let's do that first. So the longest wavelength that we can fit is going to be 1/2 wavelength fit in our cavity, right? So if we have 1/2 wavelength in there, that's the longest we can fit. Any other wavelength is obviously going to be shorter. So that means that the length of our cavity is just 1/2 the wavelength, which means that the wavelength is just 2 times the length. And here the length is 1.5 centimeters, so that will just get us a 3 centimeter wavelength. So that's like a microwave. And now what is the lowest frequency? Well, the lowest frequency is going to correspond to this wavelength here, f sub 1. So f sub 1 is c times n over 2l. So all we have to do is just plug in 3 times 10 to the 8, n is equal to 1, and then 2 times l is just 3 centimeters, so that's 3 times 10 to the negative 2. So here we can see right away that our 3's will cancel, 10 to the 8 and 10 to the negative 2, so we're just going to get 10 to the 10 hertz. Okay. So now, for a standing wave of this wavelength, where in the cavity does the electric field have the maximum magnitude? So we said it looks like this, so it's 1/2. Let me draw that a little better. So it's 1/2 wavelength. So where does E have the maximum magnitude? Well, the maximum magnitude is going to be midway, right? The maximum magnitude for the electric field will be at its antinode here, which is in the midpoint. So the midpoint, where does it have its 0? So E is equal to 0 at obviously the endpoints here because we said those are nodes. So I'll say at endpoints. And then where does B have a maximum magnitude? Well, we know that the antinodes and nodes for the electric and magnetic field are switched. So B is going to have its maximum magnitude, its antinode, at the endpoints, right, opposite the electric field. So B max is going to be at the endpoints, and B is equal to 0 will be midway. Okay, so now let's do one more example with standing waves. This one's a little bit more difficult. So here we have an air-filled cavity for producing electromagnetic standing waves, has two parallel highly conducting walls separated by a distance L. So we're just in a cavity of length L, so it looks like this. And this is length L. One standing wave pattern in the cavity produces nodal planes of the electric field, so it has nodes with a spacing of 1.5 centimeters. The next higher frequency standing wave in the cavity produces nodal planes with a spacing of 1.25 centimeters. What is the distance L between the walls of the cavity? So what is the length of our cavity? So in a cavity, we know that wavelengths of 2L over N can fit inside the cavity. And now we know that if they're telling us that nodal planes are 1.5 centimeters apart, that means that 1/2 lambda is equal to 1.5 centimeters. So half a wavelength is equal to 1.5 centimeters. So we can just multiply this equation, plug this equation in right here, and we get 1/2 2L over N. So we get that L over N is equal to 1.5 centimeters. Now they tell us the next higher frequency, so N plus 1, is going to have a spacing of 1.25 centimeters. So every half wavelength now is 1.25 centimeters. So now we have lambda of N plus 1 is going to be 2L over N plus 1, obviously. So now, since we know that the half wavelengths are 1.25, we can just say that 1/2 of lambda N plus 1 is equal to 1/2 of 2L over N plus 1, right? Because this is the wavelengths that are allowed, and we know that every half wavelength now is equal to 1.25 centimeters. So what you have to do now, so let's, we see our 2's cancel, so we have L over N plus 1 is equal to 1.25. So we have this equation and this equation, and you have 2 unknowns and 2 equations, right, L and N. So you can get rid of N and just solve for L. And I'm not going to go through the algebra for that here, but when I upload my full notes, I'll put all the algebra in for solving for L. So for now, I think, because we're probably going a little bit over, I'll just give you the answer. So when you solve for L, you get that L is equal to 7.5 centimeters. So you just solve these 2 equations, solve for L, and you get that L is 7.5 centimeters. So okay, so I know that that was maybe a lot for today. But next time we'll be doing photons, so a little bit more EM and light. But yeah, so that's it, and I will see you guys next time.